or well, let's say last time we talked about section 8.3, some of these application of vector problems, and asked you guys to work on 41 through 50. Any questions from either those problems or the previous part of the problem set? We'll start with questions. Jack? Sure. So 20 asks us to find the unit vector in the same direction as the vector indicated below, and then to write your answer in component form and linear combination form. So the formula that I'm using for a unit vector in the same direction is this one. So 1 over the magnitude times the vector. In our case, that magnitude is going to be the square root of 109. So square root of 100 squared, or negative 100 squared plus 3 squared gives me 109. And then we just scalar multiply that in. And then I'd probably rationalize my denominator since that's going to be my final answer. Cool with that? And then for part B, if I want to put that in linear combination form, all I do is I take the x component and slap on that vector I, and I take my j component and then slap, or my y component, slap on that vector j. Everybody's okay on that? Jack, you feel good? Yeah, no problem. Who's next? Robbie? Sure. I'm going to copy and paste that in, I think. So 50 says we got a crate weighing 80 pounds. That's being pulled up a ramp at an angle of elevation of 29 degrees with a force of 130 pounds. And we have a ramp with an angle of elevation of 22 degrees. What is the amount of force being directed up the ramp? So I guess the first question we'd ask is, when you guys read this, how many vectors do you hear in the question? Should be 3. So we have this vector with gravity acting on the crate. We have the force of the pull going on the crate. Then we have the ramp itself. So that's my picture. So real quick, writing down the magnitudes and directions for these. Notice in no way, shape, or form were we given a length for the ramp. So we're free to choose the length of the ramp to be anything we want. I'm going to make it a unit vector here. Now, a couple of ways we could approach this since we have three vectors. Right? So we have two vectors that are acting on the crate. We have the gravity acting on the crate and the pulling acting on the crate. So what we could do is we could project both of those vectors separately onto my ramp. But if we do that, it's not entirely clear whether we should be adding or subtracting these vectors. Now, if you think about this in a real sense, if you just set a crate on a ramp, what's going to happen to the crate? It'll slide down the ramp, right? And if you're pulling the crate, what way is the crate going to go? Up the ramp. So if you think about it in that sense, it's kind of clear that, okay, I'll subtract then the magnitude of those two projections. That's fine. What I would prefer to do, though, is I'm going to resolve my vectors G and P into component form, add them, and then I'll just take that resultant vector and project that onto the ramp, which I think is the easiest way to do it. In particular, if it's, if my second force wasn't just due to gravity, and would it maybe entirely be clear whether that crate should be going up or down the ramp. The numbers will just kind of take care of themselves that way. All right, so let's go ahead and just resolve these into component forms. Yes, sir.
So for G, is it 50?
What's up?
Is it 50 or 80?
Oh, should be 80. Thank you. So we'll go and just resolve these into component forms, just like we've done for all the other problems. And I'm writing down maybe more stuff than really like I need, but it's a question, so I don't think it does anybody any harm for me to write down maybe a little bit more than is totally necessary. So I got 11370 and 6303. Oops. And then my last one here, sine 22. And then sine 22, so 0.93 and 0.37. All right. So I'm going to go ahead and add the vectors P and G together. There's that. And then what I need then is the magnitude of the projection of that vector P plus G onto R. But since R is a unit vector, I can do this really easily by just doing the dot product instead of actually having to calculate that projection and then do the magnitude, which, I'm all about that life because it saves me a bunch of hassle. So let's see. This one times this one plus, I guess I'm going to have to use a parenthesis there because I didn't actually subtract the 80 in my calculator. So I do that, I get 9906. And because that number is still positive, we know we're moving up the ramp. Robbie, does that feel okay there? Okay. Aria. Why are we adding P plus G? Because both of those vectors are forces that are being directed into the ramp. Right? We have a force due to gravity acting on the crate that'll causing it to move on the ramp. And we have a pull vector, you know, a force due to like a rope attached to the crate that somebody's pulling that's acting on the crate. So both of those two force vectors are being projected into the ramp. It's easier to treat them as one resultant vector than to do two separate projections. So I just did it that way because it was easier. Does that make sense? Thank you. 49 is basically identical to this one, just different numbers. So if you can do 50, you can do 49. Jack?
You're able to set them equal because it's a unit vector?
I was able to do this shortcut because R was a unit vector. Yeah. If R wasn't a unit vector, then I have to go through the whole shebang and actually find the projection and then calculate its magnitude. This shortcut that I use is just because R was a unit vector. But I'm going to use that shortcut when it's available because that saves me quite a bit of hassle. Okay. Who's next? Tommy?
You do 36, but
36. So 36 wants the angle between V and W, where V is negative 4, 5, and W is the vector negative 2I plus 3J. So I would start by just converting W into component form. So the coefficient on the I becomes the X component, and the coefficient on the J just becomes the Y component. It's real easy to do. And then the angle between two vectors is going to be the cosine inverse of V dot W divided by the magnitude of V times the magnitude of W. So the dot product there, negative 4 times negative 2 plus 5 times 3 divided by, let's see, that's 16 plus 25, so that's 41. And then that's 4 plus 9, so 13. Oops, forgot my cosine inverse. And then it's just calculator time. So cosine inverse, I'm going to use the fraction command to make this a little bit easier. So I don't have to use so many parentheses. So I have 8 plus 15 over root 41 times root 13. So I get 4.96. Double check my key and make sure that's the right answer. I didn't do anything silly there. Nope. That's correct. I guess 4.97 would be the... I suppose that if we could have graphed that and gotten a good indication whether that was a reasonable answer or not, I'm suspecting they are, you know, really big tiny angle between them because that's the number we got. Been like, oh, what's this look like? It's like almost looks like a straight line. Probably the vector if you, or the two vectors if you drew them together. Okay. last call on questions here. Arya? 18? Sure. So here we have some points. And we're asked to do the vector calculation -5 times CB plus root 2 times BD. So I'm going to start by just resolving CB in component form. So I'm going to use the head minus tail rule. So I'll do head minus tail, and then head minus tail. And same thing here. So head minus tail, and then head minus tail. Feel okay? I'll do my scalar multiplication next. Again, order of operation is the same. So I want to do multiplication before addition and subtraction. Now I can't multiply a radical to a rational number. So I'm just going to do like 6 root 2 and 10 root 2. And then to add these, we just add the x components with the y component, or the x components together, and then add the y components together. But again, I can't add a rational number to a radical, so instead of, I just wrote -35 minus 6 root 2 and 65 plus 10 root 2. Suppose you could have made those decimals if you really wanted to. I would just leave it this way. Exact answer is usually preferable unless you're asking for a rounded answer. There's some context that makes a rounded answer mean, make more sense or be more meaningful. Does that feel okay, Arya? Okay. Okay. So we can always come back and ask more questions next time as you guys get further into your problem sets. No big deal. But for now, we're going to start talking about section 8.4, which is about two-dimensional vectors in space. Sounds like the title to a children's show or something. 2D vectors in space! No? I'd watch it. All right. So we're going to start here by defining another way to represent vectors. And at this point, you got to be like, it's cool, like enough already. There's enough vector representations. Like, I'm sick of it. Well, too bad. We have one more. So let's say we just have our component form vector v. We say that what our textbook is going to refer to as the IB component form. Now, when I was a student, we would have just called this a column vector, because the vector's written in a column rather than a row, but whatever. So if I slip and call this a column vector, which I probably will do the duration, that's the same thing as we're talking about IB component form. Everybody okay with that? All right. So today, our major emphasis is to talk about vector line equations. So back in the day, we would have talked about equations for lines like y equals 1/2 x plus 1, right? And we can represent that line with an equation like y equals 1/2 x plus 1, or a graph, something that would look like this. Right? The slope is positive, it's going up. The y-intercept looks like about 0, 1. And the slope is not very steep because it's 1/2 is not a steep slope. Everybody feel okay with that? Okay. So on a line like this, we can generate as many points as we want by doing something like picking a value for x and finding the value for y. So if we pick x equals 2, we'd get the y value of 2. So maybe here's our point 2, 2. Right, so we can do things like this with an equation for a line. And it's easy to check to see if a point lies on a line like this because you just plug in the x value and make sure it matches the y coordinate for the point, right? Obviously 2, 5 wouldn't be a point on this line because when you plug 2 in for x, you get the y coordinate 2, not 5, right? So let's just pretend that instead of talking about the specific point 2, 2, we're just going to talk about some arbitrary point p naught. So that's a p with a 0 as a subscript or a letter O as a subscript. It doesn't, they look the same on your sheet of paper. We read that as p naught, N-O-T. So what we're going to want is a way to represent a vector equation to describe the same thing as this line. So if I have some arbitrary point, I need a vector to kind of do this, or a vector to kind of do that, right? So when we wrote a equation for a line way back in the day, we needed like a point and a slope, right? So to write a vector line equation, we're going to need a point vector and a direction vector, which is basically like a point and a slope. So if I have the point 2, 2, that would be analogous to the point vector 2, 2. Oh, big whoop, Mr. Kulik. Yep. So the slope for our equation is what? 1/2, right? And back in the day, how did we calculate the slope? Rise over run, okay. Or specifically, yeah, change in y over change in x. I like that. So I'll call my direction vector v, and the direction vector is going to be 2, 1. Why 2, 1? Because the x component is on top and the y component's on bottom. So if slope is change in y over change in x, the direction vector should be the change in x over change in y. Everybody's okay with that idea? Okay. But that's still not quite what we want, because I need to be able to generate any point vector on this red line. So I need to somehow be able to make this part of my vector line equation as long or as short as I need it to be. So what I'm going to do is I'm going to include a scalar that I'm going to attach to the direction vector. Remember that scalar multiplication doesn't affect direction, right? It's just going to change the length of the vector, but it wouldn't change the direction of our vector. At least, well, I mean, it could make it opposite direction if you multiply by a negative, but it's still going to, for our purposes of having a line, whether it's pointing this way down the line or that way down the line is okay. Everybody's okay with that? So our vector line equation then, we're going to write as R equals R naught plus VT, where R naught is our point vector and V is our direction vector. And since t is just a real number, right, t is a scalar, so t can be positive or negative, so it can give us, you know, the positive half of our line or the opposite direction negative half of our line. Everybody's cool with that? So awesome. We got this, you know, this new vector line equation. That's great. So first things first, let's talk about how we can go and convert from a slope-intercept equation to a vector line equation. Okay. So to write a vector line equation, I need a point vector and a slope vector, or a direction vector, excuse me. Correct? So to generate those, I'm just going to take some point on my line. So what's an example of a point on this line? 0, 5. I would use the y-intercept also. That seems to make a lot of sense. Which gives me my point vector then. Zero, 5. That's really easy. What's the slope here for my line? 3. I'm going to write that as 3 over 1 though. That'll give me my direction vector, which would be 1, 3. Make sure you're not writing it as a fraction, right? This is a vector, not a fraction, so make sure you're being careful there. That's a common mistake. Okay, so now I have everything I need. And there's my vector equation for a line. Is that the only way I could write it? No, man. How many different versions of this do I have? Infinitely many. Why infinitely many? Yeah, we have infinitely many points. And the slope 3, 1, I could have written as negative 3 over negative 1, or 6 over 2, or 3 over, 9, or 9 over 3, or and kept going and going, and there's like an infinite number of ways to represent that slope piece, right? So this is just one possible vector equation for this line. There's infinitely many correct answers to this. Okay, so this is where we've written our vectors in IB component form, right? Yes, of course. What if I wanted to write this with my vectors in linear combination form. So reminder again, linear combination form is that thing with the i's and the j's. So if I take this, that first vector becomes 0i plus 5j, and my second vector would become 1i plus 3j. Everybody feel okay with what I did there? And then what we'll do now is we will get the I parts together so we can factor an I off, and then the J parts together so we can factor the J off. Everybody okay with that? Just did a little rearranging. And now that I have a vector line equation, I could ask, is, say, the point 2, 6 on that vector line equation that we just wrote? So to check that, what we really want to see is if there's a single value of t that can generate that 0.26. So what we kind of do is we're just going to replace the r, the vector r, with the vector 2, 6. And then we're going to do the vector operations on the left. So if I do the scalar multiplication with t and then add the vectors, I would get the vector 0 plus 1t and then 5 plus 3t. Does everybody kind of see what I did there? So then what I'm going to do is I'm just going to check and see. So when I solve this one, I get t equals 2. When I solve this one, I get t equals 1/3. I'll note that these are not the same value of t. That tells me no, 2, 5 is not on the line represented by that vector line equation. Yes. Not. Oh, yes. Thank you. Does everybody feel okay so far? Again, none of the things that we're doing are tremendously difficult from like a symbol pushing aspect, right? It's just making sure that we're comfortable with the notation, understanding like what things mean. You know what I mean? Okay. What if we wanted to do the reverse? What if we wanted to say we wanted to write the vector equation in slope-intercept form. Again, slope-intercept is y equals mx plus b, just as a reminder. Again, I know you know this, but sometimes it helps to remind us. To write an equation in slope-intercept form, we need two pieces of information. Either we need slope in a point or 2 points. I can generate either from this vector line equation. All I need to do is pick two different values for t. That'll give me two different points. Or what I would prefer to do, from my point vector, I can read the point 1, 3. From my direction vector, I can read the slope 3 over 2. And then I can just plug that into y equals mx plus b to solve for b. So it's that going to be 11 over 2 then when I add that over. It's super easy, right? It's basically like an Algebra 1 problem. Lexi?
Yeah, 3, 1, 4, 1.
Oh. Oh, yeah. Yep, no. Thanks. Oh, well, that just becomes negative. It's not a big deal. Easy fix. Thank you. Appreciate it. Yes, you're absolutely right, though. But again, very easy process, right? This is like an Algebra 1 or pre-algebra type problem. Once you've ascertained the slope and the point, it's like, oh, I've done this like 1 trillion times in my mathematics career. That's not so bad. Okay. The last thing we need to talk about in this section is finding the intersection between the two vectors or vector line equations R1 and R2. Oops. Need to have R2 there. So one thing to say right out front is that we're going to acknowledge the fact that you could do what we just did and convert these both into slope-intercept form and then solve your system like we would have in an Algebra 2 class. That's fine. That's valid. It works. I'm not going to show you using this method or that method because what we're about to show you scales much better if you have more than 2 variables and becomes subroutines in future things that we're going to do. So I'd encourage you to do it the way I'm about to show you and not try to do the Algebra 2 way. Everybody's okay with that? Particularly if this gets to 3 dimensions, like the direction is no longer, there's no slope in 3-dimensional line equations. So it's like kind of a whole different thing. You know what I mean? So while that's a nice patch in 2 dimensions, it doesn't hold for very long. Okay, So if we talk about an intersection between the two lines, what we're talking about then is a point vector that's on R1 and also on R2. Everybody agree with that? So let's say we have the vector xy that's on R1 and the vector xy that's also on R2. I'm going to go ahead and do my vector operations. To simplify this sum of two vectors into a single vector. Is everybody okay with what I did there? Pretty easy so far, so good. So what I have is that x is equal to 2 plus 1s, and I also have that x is equal to negative 1 plus 3t. So since they're both equal to x, we can say they're equal to each other. And then similarly with y. And we know that to be able to get the point xy, that value for s has to satisfy both equations simultaneously, and the value for t has to satisfy both equations simultaneously. So this is really a system of two equations that we're solving now. So what I would start by doing with my system is setting it up into kind of that standard linear form. So I'm going to subtract 3t from both sides of the first equation, and then subtract 2 from both sides to get the s and t on one side and the constant on the other. And then we'll do the same thing in this second equation by subtracting 5t from both sides, and then subtracting 4 from both sides. Everybody's okay to here? Now think back to your Algebra 2 class and remember, what's the easiest and fastest way to solve a system like this? I would say there's one better than elimination. One better than substitution. I would use a matrix and do row reduced echelon form because I can do this entirely on my calculator. That would be the choice that I would make so that it becomes not a by hand calculation. Sound good to you guys? All right, let's review how we do that. So if you want to follow along, you can take out your calculator. All right, so we'll start by going into the matrix menu. So I'm going to press second and the x to the negative 1 button to open the matrix menu. To enter a matrix into my calculator, I'm going to move over to the Edit tab, and I'm going to select a matrix. I'm going to use matrix C for us. The first thing I need to do is assign a dimension to my matrix. So my system here has 2 rows, and I'm going to need a column for the s's, a column for the t's, and a column for the constant that it equals. So I'm going to need 3 columns. Now the entries in my matrix are just going to be the coefficients from my system. So I'm going to have 1, and then -3, and then -3, and then 3, and then -5, and then 1. So my matrix should look basically identical to my system, right? The only thing that's missing are the symbols, the variables, but I have all the numerals there. Everybody's okay? Once I've done that, I'm going to exit back to the main screen. So press second and then mode. And then I'm going to go back into the matrix menu. And this time I'm going to move to the Math tab. I'm going to scroll all the way down to the bottom and select the RREF command. RREF stands for Row Reduced Echelon Form. It basically, the calculator is programmed in a process called Gauss-Jordan elimination that's going to take any matrix that's in this form and rewrite it in a way that the solutions to our system just kind of fall out of it. It's basically doing the same thing as our elimination did by hand, but it's a programmed algorithm. So I'm going to press enter on RREF. Make sure you pick RREF and not REF. And then I'm going to use that command, RREF, on the matrix C. So I'm going to go back into my calculator, select back into the matrix menu, and from the names tab, I'm going to select that matrix C that I just made, and then press enter. I'm going to take a minute and just kind of write down a little bit of work of what we just did. Notice that we got a decimal here at the end. You can still use the math and fraction command on a matrix to give it back to you as fractions. In this case, it doesn't really matter that it's decimals rather than fractions, but you don't want to be rounding if you don't have to do this sort of thing, because it won't exactly work out for you. Okay, now somehow Mr. Kulik says that the answer, the solution to my system is given to me by this matrix. So this is the way we interpret that. This first row is representative of an equation. Remember, the S's were in the first column, the T's were in the second column, and then equaled the answer. So this first column reads as first row reads as 1s plus 0t equals 9/2, or just that s is equal to 9/2. Similarly, the second row would be 0s plus 1t equals 5/2, or just that t is 5/2. Okay? Now, super important, the point of intersection is not 9/2, 5/2. What the S and T would allow us to do is it tells us the value for S and T that give us the point of intersection. So I'm just going to pick one of them. So I'm just, for the sake of argument, going to pick S. And then I'm going to find the equation for a line that involved that parameter S. And I'm just going to plug that in and simplify. So here's a place where we have to be real careful. Notice that 1, 3 is a vector. 9/2 is a scalar. So we're doing scalar multiplication there and then adding the vector 2, 4. So 9/2 plus 4/2 gives me 13/2. And then 27/2 plus 8/2 gives me 35/2. So there is my point. Absolutely. Again, I acknowledge that it would have been easier to put these both in slope-intercept form and just solve it the old Algebra 2 way. The reason we're doing this is that this routine that we've just built up works exactly the same if it's 2-dimensional or n-dimensional. It's still going to work the exact same way, which is lovely. And in fact, it gets easier the bigger things get because it's the exact same steps. Your matrix is bigger, but big frickin' whoop. That doesn't matter to us because we're just using the calculator to solve the matrix anyways. So just to kind of reiterate what we did here is we expressed our vector line equation in terms of an x and a y component. We found the equation for the x component and y component in the first equation, and the x component and y component in the second equation. We set the x's together and the y's together, formed a system, solved that system with a matrix, and then used the solution back into the corresponding line equation to generate my point. Cool? Maybe. It's difficult. It's a lot of things to kind of keep straight, but here's the thing. If you understand like what the things are representing and like what's a vector and what you can do with the vector and what you can't do, it's not a difficult procedure. It's unfamiliar looking and strange right now, but it's not really that difficult. Alexis?
How did you get the 13 and 35?
So 9/2 times 1 is 9/2 plus 2 is 4/2. So 9/2 plus 4/2 is 13/2. And then 9/2 times 3 is 27/2. Plus 8/2 is 35/2. So I just did, again, the tricky part there, the place that's easy to make mistake is you have a scalar and then you have a vector. One of them there's a fraction bar, the other there's no fraction bar. It's easy to kind of mess that up. Okay. This, to me, feels like a good place to stop. The next section, we just build on these ideas. I feel like you probably need a chance to let this sink in a little bit. At this point, you should be able to do 51 through 76. Notice that this 51 through 76 is going into next week's problem set, not Sunday's problem set. So Sunday, you're just looking at 1 through 50. 51 through 76 is going into next problem set.
Aiden, can you go backwards?
I'd also like to point out to you guys, that We didn't do the homework quiz today, which I told you is probably coming soon. The odds of a homework quiz next time have gone up or down? Up. At this point, what
are the biggest odds?
At this point, what sections would the homework quiz cover? 1 through 3. The 3 sections we've talked about so far.
Four is easy.
Is that-
Okay.